Thank you, RDPR fellows. Uh, Next up, we have fellows from CDAC. CDAC was an interesting experiment in which we have a design fellow, a GIS fellow, a data science fellow, and a full stack engineering fellow, all four of them working on the same problem statement and all four of them approaching it from their own viewpoints. So it's a great example of what interdisciplinary teams can achieve in the government and a small glimpse of it. So over to you, Benny.
Thank you, Harsh. Good afternoon, everyone. We are here today to present our work on Emergency Response Support System of India 112, deputed at CDAC Trivandrum. Our team, myself, Abhishek, Aryan, Aditya, Sukriti, who are focusing on various tracks, design, full stack, data, and GIS. CDAC is an R&D organization under the Ministry of Electronics and Information Technology for developing and deploying advanced computing, IT, electronic solutions across various sectors, and 112 being one of their key nationwide project. 112 Emergency Response System is an integrated all-in-one helpline for immediate support during emergencies. It unifies police, fire, medical services via a centralized control room, and the system tracks real-time location, dispatch, and communication. Let's take an example. Imagine you yourself as a citizen having to face an emergency situation. And if you've called 112 and explained the issue that the caller to the caller, but you're panicked, anxious, waiting for the response of the call. And later, after some time, the help comes to you. The goal of the project is to improve this experience of the citizen who makes an emergency call. The experience includes the time taken for the help to reach and also not having to repeat the information that you've once shared. The citizen interacts with the caller and gets to see the vehicle as it comes for help. But the process is not this simple and straightforward as you see. The system is actually much more complex in terms of information flows. To understand this, we had to map the entire system, the system blueprint, to understand people and processes. Such a detailed level of mapping not just helped us to understand the user flow, but also the incentives and the task of different people involved at different layers. From there, we moved on to understand how people interact with the system and also the interface. Each person had its own task and an interface that helped them achieve this task. Multiple site visits and qualitative interviews led to helping us understand the nuances of the system from a user perspective and how they navigated different challenges during the processes. Multiple, we also tracked eye patterns to understand why and how much time was taken for each interface. All of the study helped us understand few observations and challenges. Challenge 1. The call initially made by the victim has one of the richest data set, but the incentive of the CRM was to close the transaction in the shortest period of time, due to which the key information gets lost. Challenge 2. As the CRM was incentivized for the time taken, this often leads to marking the wrong incident location and which ends up being the police station rather than the actual location, which makes it harder for the people down the loop who end up making multiple calls to the victim who's already anxious to identify what the correct location is. Challenge is 3. The petrol vehicle, which is not very same on every single day. They fluctuate with respect to the duties that come up. So better allocation of vehicles was needed with respect to the current day availability, which helps us understand and better their response times. Why these challenges needs to be addressed? This is not to make sure this is to make sure that the victim who is in the state of anxiety, distress, has a better user experience, and then the CRM can be more humanely present. As Uma ma'am was mentioning, the human does the most human role in the system, and the technology supports it.
Now we will dive into the first challenge, which is the loss of information. So can we use AI to extract the structured information from the calls itself, saving time for the CRM? Our priority was that the model should be open source, it should be on premise and having low latency. Emergency call centers receive a huge number of calls that often have background noise and fast informal speech. To make these calls useful for quick decision making, we need to convert the audio into accurate readable text. Our first task was to identify the speech to text model that can do this with the least loss of information. We received over 4,000 emergency call recordings from Uttarakhand's public safety answering point for our analysis. I manually annotated around 10 calls to figure out the accuracy. But to strengthen our benchmark, we added Gramvani dataset of telephonic Hindi audio. After cleaning and standardizing the text, we evaluated different open source along with some proprietary models for the sake of benchmarking, like AI for Bharat, Whisper, Sarvam, and Google Speech. Multimodal LLMs were not included in our evaluation. This is a scatter plot for the word error rate versus the latency. It shows how each model performed in terms of accuracy and speed. The models closer to the bottom left corner are both fast and accurate. So according to this plot, AI for Bharat's Bhashini stood out as the best overall performer for real-time Hindi emergency call transcription. And the fact that it is open source makes it the definitive winner.
So the second part of our pipeline addresses the next challenge. Even with an accurate transcript, the text is not so clean. It's unstructured nodes where critical details get lost. To solve this, we introduce open source LLM pipelines. It automatically reads the raw text and extract key details into a clean, structured format, making the data instantly actionable. To build a reliable pipeline, we had to find the best model. We tested multiple on-device open source models like Llama, Gemma, Phi. We evaluated them on manually annotated ground truth datasets using various metrics. As the charts on the left shows, we analyzed their completeness versus processing time to select the best model that is both fast and accurate. We also confirmed a key strategy shown on the right, that is translating Hindi to English first dramatically reduces errors, ensuring a highly reliable outcome. This high quality data also allows us to improve the system's core schema. We analyzed hundreds of calls that were vaguely labeled as others, which was a major blind spot. As the model learned, it automatically discovered these important new event subtypes like financial disputes and public intoxications. This provides valuable model driven insights to expand and enrich the official schema for more accurate data collection in the future. So, to bring it all together, this is our complete pipeline from ingestion and processing by the STT model to LLM extraction of structured data, and finally to the analysis. This extraction of structured data allows us to solve the next challenge, systematic and accurate marking of locations. The demo in the
The audio on the demo is not visible, so you can just speak over it to explain what's happening.
Yeah, so in this video, there is a call made from the caller to the call taker. So the moment the call transcript is generated, the information is structurally extracted and the map automatically zooms to the location mentioned in the call. So as you can see, the transcript is generated and the structured information is taken out and the location is zoomed. So by automating this process, we not only speed up the response, but also free up the call taker to be more present and compassionate with the person in distress.
The third problem which we discovered was that number of available patrol vehicles keep changing, and this leads to the static allocation often fluctuating and or fluctuating incident response time. To solve this, can we dynamically allocate patrol positions for police vehicles on a daily basis based on past patterns? To do that, we first needed to analyze past trends and find the true locations of incidents. The challenge we identified was that around 35% of incidents are tagged to nearby police stations rather than where the crimes actually occurred. To correct this, we created a buffer of 250 meters around the police stations, took those incidents and redistributed them based on proximity to population density and urban activity areas, giving us a more realistic spatial pattern of crime occurrences. Now we tried to map patterns these incidents followed. Spatially, public disturbance incidents were most prevalent near hospitals, schools, and colleges in the city center. A rise was seen near religious places around the city. We also discovered that hotspots change temporally. In the city center, the hotspots change as we move ahead in the day. The intersections, which were hotspots in the morning, gradually became cold spots by night. Now we moved on to the resource allocation phase. The goal here was to optimize the deployment of police patrol vehicles so that they can respond quickly to incidents. We first built a cost matrix using the road network to represent travel times between demand points and potential facility locations. Then we applied the P-median model, which aims to minimize the total weighted travel time or distance between crime hotspots and police units. Each demand point is weighted by incident frequency or severity to take optimal allocation into consideration and to cover potential crime sites optimally. This video shows how average response time increases when the MDT locations are decreased from 10 to 6 in the city of Trivandrum. At the end, we'd like to thank Mr. Santosh and Mr. Jose from CDAC Trivandrum for their constant guidance and support throughout our summer. We are grateful to the entire ETG team for making us feel welcomed all the time, and the entire Bharat Digital team, Harsh, Richa, Vinamra, and Sabita, for their constant guidance and support. Thank you.